Close your eyes for just a moment. Imagine standing in a field at dawn, watching the first light touch the horizon. Feel that warmth on your face, that ancient warmth that has kissed every generation of humans who ever lived. Now, imagine it gone. Welcome back, Midnight Travelers. I'm so glad you're here with me tonight. This is the Midnight Explorer, and tonight we're going to take a journey together, a journey into darkness, into wonder, and into one of the most profound questions humanity has ever pondered. What would happen if the sun simply disappeared? But this isn't just a story about physics or astronomy. No, tonight we're going to trace something deeper. We're going to follow the thread of human consciousness itself. How we came to understand that glowing disk in the sky, how we measured its distance, how we discovered that light itself has a speed, and what that realization meant for everyone who came after. So settle in, pour yourself some tea, dim the lights. Because tonight, we're not just exploring space, we're exploring time, memory, and the 8 minutes that separate us from the star we call home. Let's begin. It's 40,000 years ago. A young woman stands outside a cave in what will one day be called France. The sun is setting, painting the world in shades of amber and rose. She doesn't know about hydrogen fusion or electromagnetic radiation. She doesn't know that the light touching her skin left the sun's surface 8 minutes ago. But she knows something. She knows that when that bright circle disappears beyond the hills, the cold comes, the darkness comes, and with it, the fear. For hundreds of thousands of years, humans watched the sun with a mixture of reverence and terror. It was, quite literally, the difference between life and death. When it rose, the world became knowable. When it set, the world became mysterious, dangerous, unknowable. Our ancestors didn't just watch the sun, they worshipped it. In Egypt, Ra sailed across the sky in his golden boat, battling the serpent of chaos each night to ensure his return. In the ancient Americas, the Aztecs believed the sun god Huitzilopochtli needed human sacrifice to maintain his strength for this daily battle. In Japan, Amaterasu hid herself in a cave, plunging the world into darkness until the other gods could coax her back out. Every culture on every continent created stories about the sun, because every culture understood viscerally that this burning disk was not optional, it was everything. The ancient Greeks called the sun Helios, and they imagined him as a charioteer dragging light across the dome of the sky. This wasn't ignorance, it was poetry, philosophy, an attempt to make sense of the most important object in existence. The Greeks understood that the sun was powerful, that it was distant, that it governed the seasons and the days. But they didn't know how distant. They couldn't imagine. In the 3rd century BCE, a mathematician named Aristarchus of Samos did something remarkable. Using geometry and observations of lunar eclipses, he attempted to calculate the distance to the sun. His answer was wrong, dramatically wrong, but the attempt itself was revolutionary. He suggested the sun might be about 19 times farther away than the moon. It was an estimate, and not entirely accurate, but it was close enough to prove that light is not instantaneous, close enough to prove that we are always looking into the past. Let's jump forward in time. It's 1676 and we're in Paris, at the Royal Observatory. A Danish astronomer named Ole Romer is pacing in frustration. For months, he's been observing Jupiter's moon Io, watching as it disappears behind the giant planet, and then re-emerges on the other side. He's been timing these eclipses with meticulous precision, making note of exactly when Io should reappear based on its orbital period. And here's the problem. The timing is wrong. When Earth is moving away from Jupiter in its orbit, Io's emergence appears to happen later than predicted. When Earth is moving toward Jupiter, the eclipse happens earlier than predicted. Other astronomers have noticed this too, but they've dismissed it as observational error, or perhaps some irregularity in Io's orbit. But Romer sees something else. He sees something that will change our understanding of reality itself. What if light takes time to travel? It seems absurd. Light appears instantaneous, doesn't it? When you flip a switch, the room illuminates immediately. When the sun rises, its light floods the world in what seems like an instant. How could something so apparently instantaneous have a speed? But Romer's mathematics are compelling. If light has a speed, if it travels at some finite velocity, then when Earth is farther from Jupiter, the light from Io has to travel a greater distance to reach us, causing the eclipse to appear later. When Earth is closer, the light has less distance to travel, and the eclipse appears earlier. Romer calculated that light takes about 22 minutes to cross the diameter of Earth's orbit. It was an estimate, and not entirely accurate, but it was close enough to prove that light is not instantaneous, close enough to prove that we are always looking into the past. The scientific community was skeptical. Some dismissed his findings entirely. The great Italian astronomer Cassini, his own colleague, rejected the idea. But others, Newton among them, found the concept compelling, even revolutionary. Because if light has a speed, then everything changes. The stars we see at night, we're seeing them as they were years, decades, centuries, even millennia ago. The sun we see in the sky, we're seeing it as it was 8 minutes ago. We are time travelers, all of us, every moment of every day, looking backward into history with every glance at the sky. Over the next 2 centuries, scientists refined Romer's discovery. In 1728, James Bradley provided additional evidence through the observation of stellar aberration. In the 1800s, physicists like Hippolyte Foucault and Léon Foucault measured the speed of light with increasing precision, using mirrors and rotating cogwheels and the fierce precision of human ingenuity. By the late 19th century, we knew light travels at approximately 299,792,458 meters per second, or to put it in terms that feel more comprehensible, about 186,282 miles per second. In 1 second, light could circle the Earth more than 7 times. In 1 second, it could travel from New York to Tokyo and back more than 20 times over. And yet, at this incomprehensible speed, it takes 8 minutes and 20 seconds for light to travel from the surface of the sun to the surface of the Earth. Think about that distance. The sun is about 93 million miles away from us. 93 million miles of empty space, of vacuum, of darkness. And across that vast gulf, light travels. Light that was born in the nuclear furnace at the sun's core, that fought its way through layers of plasma over tens of thousands of years, that finally escaped from the surface and streaked across space to touch your face on a summer morning. That light is 8 minutes old when it reaches you. 8 minutes and 20 seconds. Which means that if the sun disappeared right now, we wouldn't know for 8 minutes and 20 seconds. So let's imagine it.
Let's walk through this thought experiment together, slowly, carefully, because this is where science becomes poetry, where physics becomes philosophy. It's a Tuesday afternoon, perfectly ordinary. The sun is shining, or at least it appears to be shining. You're going about your day, unaware that 93 million miles away, something impossible has happened. The sun has vanished. Not exploded, not dimmed, not changed, simply ceased to exist. One moment it was there, a roiling ball of hydrogen and helium undergoing nuclear fusion, and the next moment, it was gone, leaving nothing but empty space where a star used to be. But you don't know this yet. You can't know this yet. Because the last light the sun emitted before its disappearance is still traveling toward Earth. It's racing across space at 186,282 miles per second, carrying the image of a sun that no longer exists. For 8 minutes and 20 seconds, the universe is playing a trick on you. You're living in a ghost world, illuminated by ghost light, seeing a star that isn't there anymore. Let's slow down time and walk through what happens moment by moment. Minute 1. The sun disappears. In the unimaginable silence of space, there's simply an absence where a star used to be. The inner planets, Mercury, Venus, Earth, Mars, continue in their orbits, held by the gravitational field that still emanates from where the sun was. But this won't last. Here's something Einstein taught us. Gravity, like light, has a speed. It propagates through space at the speed of light. When the sun disappears, its gravitational waves, the distortions in space-time that hold the planets in orbit, begin to dissipate outward at light speed. But we're still orbiting. For now. On Earth, nothing has changed. The sun shines in the sky. People are at work, at school, having lunch, walking their dogs, completely unaware that they're living on borrowed time. Minute 2. The last light the sun emitted before its disappearance is halfway to Earth now. It's passing through the inner solar system, crossing millions of miles of emptiness. If you were somehow able to be out there in space between the sun's former location and Earth, you could watch the boundary of darkness approaching, a sphere of expanding absence moving outward at the speed of light. Behind the wave, darkness. Ahead of it, the ghost light of a dead star. On Earth, still nothing. The sky is blue, the sun is warm on your face, birds sing, life continues. Minute 3. 3/8 of the way through our grace period. In mission control rooms around the world, satellites are taking measurements of solar radiation, monitoring solar flares, tracking the sun's magnetic field. None of them detect anything unusual, yet, because they're measuring light that left the sun before it disappeared. We're watching a replay, a recording, the last will and testament of our star. Minute 4. Halfway there now. In telescopes and observatories, astronomers are studying the sun, measuring sunspot activity, tracking the 11-year solar cycle. They're looking at a sun 4 minutes dead, carefully noting details of a star that no longer exists. There's something profoundly haunting about this, isn't there? The way information travels, the way reality itself has a speed limit. We pride ourselves on living in an age of instant communication, of real-time information, but the universe operates on a different schedule. The universe says, patience. Wait. Everything takes time. Minute 5. 5 minutes since the disappearance. The boundary of darkness is 3 minutes away now. Perhaps some distant space probe, far beyond Earth's orbit, is the first to detect the change. Its instruments register a sudden absence of solar radiation. It begins transmitting this information back to Earth, but those signals travel at the speed of light too, so Earth won't receive them in time. We are alone with our ignorance, surrounded by light that lies. Minute 6. 6 minutes. 2 minutes remain. If you could somehow watch from space, you'd see the dark sphere approaching Earth like a wave, like a tsunami of absence. Mercury has already been swallowed. Venus is about to be engulfed. Earth is next. But on Earth's surface, the sun still shines. In Tokyo, it's early Wednesday morning. In London, it's late evening. In New York, it's afternoon. In thousands of languages, in millions of conversations, people are talking about everything except the fact that their sun is gone. Minute 7. 1 minute remains. The last of the sun's light is racing toward Earth. Photons that left the sun's surface just seconds before it disappeared are now crossing the final miles. Venus has gone dark. The boundary is approaching Earth's orbit, and still we don't know. We can't know. We're waiting for a messenger who carries the worst news in the history of existence. Minute 8. 30 seconds left. The last photons are crossing the moon's orbit. People who happen to be looking at the sun, perhaps through solar telescopes, perhaps accidentally, perhaps in worship or wonder, are seeing the last true light. 20 seconds. 10 seconds. 5 seconds. And then the sun vanishes from the sky. Not gradually, not with a dimming or a fading. One moment it's there, and the next moment it's not. The blue sky doesn't darken slowly. It flips off like a switch. 1 second it's day, and the next second it's night. But not a night like we've ever experienced. Not a night with stars and moon, because the moon is dark too. The moon has no light of its own. It only reflects the sun's light, and there is no more sunlight to reflect. The moon is just a dark circle in the sky, invisible against the darkness. And the stars, oh, the stars, they're there. Suddenly visible, because there's no sunlight to drown them out anymore. In the middle of the day, on a Tuesday afternoon, the stars appear. The Milky Way stretches across the sky in all its glory. Planets are visible. Jupiter bright, Mars red, Venus and Mercury invisible now because they have no sunlight to reflect either. For a moment, just a moment, it might be beautiful, awe-inspiring, the sudden appearance of a night sky in the middle of the day. People stumble out of buildings, pointing, shouting, filming on their phones. What's happening? Is this an eclipse? But eclipses are gradual, and this was instant. And then the temperature begins to drop. Not immediately. Earth's atmosphere holds heat, like a blanket. But without the constant input of solar radiation, that heat begins to dissipate into space. The average temperature on the Earth's surface is about 57 degrees Fahrenheit. Within hours, it begins to fall. But let's not get ahead of ourselves. Let's stay in this first moment, this first second, this first minute of darkness. Around the world, chaos erupts. Not because everyone immediately understands what's happened, how could they, but because humans have never, in all of history, experienced anything like this. The sun doesn't just disappear. It's impossible. It's unthinkable. Traffic lights continue to function powered by electrical.
Imagine you're on a carousel, holding the safety bar as you spin in circles. Now imagine someone cuts the bar. You don't continue spinning. You fly off in a straight line, tangent to the circle you were traveling. This is exactly what happens to Earth. For 8 minutes and 20 seconds after the sun disappeared, Earth continued in its orbit because it was still held by the sun's gravitational field. But once that gravitational influence vanishes, once the ripples of the sun's disappearance reach Earth, we're no longer bound. We fly off into space in a straight line at about 67,000 miles per hour. That's Earth's orbital velocity. And without the sun's gravity to curve our path into a circle, we simply continue in whatever direction we were traveling at the moment the gravitational waves reached us. We become a rogue planet, untethered, flying through the darkness of space with no destination, no anchor, no home. But would we feel this? Would you, standing on Earth's surface in that first moment of liberation, feel anything? No. Nothing at all. This is one of the strange mercies of physics. We don't feel Earth's motion through space. We never have. Right now, at this very moment, you're moving at 67,000 miles per hour around the sun, and you feel completely still. You're moving at 1,000 miles per hour as Earth rotates on its axis, and you feel completely still. So when Earth breaks free from its orbit and begins flying through space in a straight line, you feel nothing. The ground doesn't shake. There's no lurch, no sensation of acceleration. You simply continue standing or sitting or lying down, completely unaware that your entire planet has become a spaceship flying through the void with no captain and no destination. But there are things you would notice. Things that would become apparent quickly. The stars would start to shift. Not dramatically at first, not in a way that anyone except an astronomer would detect in the first hours or days, but Earth's motion through space would now be taking us away from our former orbital path, and the positions of the stars, which have been stable reference points for all of human history, would begin to change. Within weeks, the constellations would look different. The North Star would no longer be north. The careful maps that ancient navigators used, that Polynesian voyagers memorized, that guided humans across oceans and deserts for thousands of years, all of them would become obsolete. The sky itself would become unrecognizable. But in the first hours, in the first days, most people wouldn't be looking at the stars. They'd be dealing with more immediate problems. The temperature is falling, fast. Without the sun's constant input of energy, Earth's surface temperature begins to plummet. Remember, space is cold. Not cold like winter, not cold like the Arctic, cold in a way that's hard to comprehend. The average temperature of empty space is about negative 270 degrees Celsius, or negative 454 degrees Fahrenheit. That's just a few degrees above absolute zero, the point at which atoms themselves nearly stop moving. Earth's atmosphere provides some insulation, some buffer against this cold, but it's not enough, not nearly enough. Within a week, the average temperature on Earth's surface would drop below freezing. Within a year, it would drop to negative 100 degrees Fahrenheit.
Within a few years, the atmosphere itself would begin to freeze and fall as snow, nitrogen snow, oxygen snow, the very air we breathe crystallizing and drifting to the ground like some apocalyptic precipitation. The oceans would freeze, first the surface, then deeper and deeper layers. Eventually, given enough time, the oceans would freeze solid all the way to the bottom, miles of ice, entombing everything that lived within them. But perhaps the most immediate problem, the most pressing crisis, would be simpler: darkness. Humans need light. Not just metaphorically, not just symbolically, we actually, biologically need light. Our circadian rhythms are governed by light. Our mental health is influenced by light. Our very sense of time and place relies on the cycle of day and night. And now there would be no day. Ever again. Just an eternal night, broken only by the artificial lights that we create. Lights that require power, require energy, require resources that would become increasingly difficult to maintain. Let's pause here for a moment. Let's step back from the physics and the catastrophe and think about something more human: memory. There's a question that philosophers and psychologists have debated for centuries. How much of our humanity is tied to the sun? How much of who we are, our cultures, our languages, our stories, our very sense of self depends on that bright disk in the sky? Think about how many of our words and concepts are built around light and darkness. We talk about dark times and bright futures. We describe knowledge as enlightenment and ignorance as being in the dark. We say we're looking for light at the end of the tunnel, or that things are looking brighter, or that someone is a bright light in our lives. These aren't just metaphors. They're deeply embedded in our consciousness, in the way we process and understand reality. Light is good. Darkness is frightening. Dawn is hope. Sunset is ending. What happens to a species that evolved under a sun when that sun disappears? Not just physically, we've talked about that, the cold and the darkness and the death of plants and the freezing of oceans, but psychologically, spiritually, what happens to the human soul? There's a condition called seasonal affective disorder, SAD, where people experience depression during winter months when sunlight is scarce. Imagine that, but permanent. Imagine the last sunrise humanity ever sees and how it would replay in people's minds like a lost home movie, a memory of warmth and light that becomes more precious and more painful with each passing day. Children born after the sun's disappearance, if any humans managed to survive that long, would grow up in darkness. True, complete darkness broken only by artificial light. They would hear stories about the sun the way we hear stories about dragons or unicorns, fantastical tales of a glowing ball in the sky that provided warmth and light and made plants grow. Would they believe it? Or would it seem like mythology, like the stories ancient humans told about gods and creation? Impossible to verify, impossible to prove. There's something deeply melancholy about this, isn't there? The idea that something so fundamental to existence could become a myth, that the sun itself could become a legend, a story told in the dark to give people hope or context or a sense of history. But let's think about this differently. Let's think about what humans might preserve. In the first hours after the sun's disappearance, once the initial shock wore off, once scientists confirmed what had happened, there would be a race, a desperate race to record everything we knew about the sun. Every measurement, every observation, every photograph, every piece of data collected over centuries of solar astronomy. Museums would become time capsules. Art galleries would carefully preserve every painting that featured the sun, every sunset Turner painted, every sunrise Monet captured, every ancient Egyptian papyrus showing Ra's solar disk. These would become priceless, not for their artistic value, but as historical documents, as evidence that the sun once existed. Music would take on new meaning. Every song about sunshine, every hymn to dawn, every piece of music inspired by light would become a memorial. Children would learn Here Comes the Sun, not as a cheerful pop song, but as a requiem, a lament for something lost. And photographs. Oh, the photographs. Every casual snapshot taken in daylight, every family photo on a sunny beach, every selfie snapped in golden hour light would all become treasures, because they would show what the world looked like in daylight, what human faces looked like illuminated by that singular source of natural light. We would become archivists of light itself, desperately preserving the memory of something we took for granted, something we thought would last forever. But here's where the thought experiment becomes even more complex, even more philosophically rich. What if we could survive? What if, somehow, humanity found a way to persist without the sun?
It sounds impossible, doesn't it? How could humans survive without the sun? We're creatures of light, descendants of beings that evolved under that star's warmth for billions of years. Every atom in our bodies was either forged in stellar nucleosynthesis or created from elements that were. We are quite literally made of stardust, made by stars, made for a life in the light. But humans are also remarkably adaptable. We're problem solvers. We're survivors. And in the first days after the sun's disappearance, that ingenuity would immediately kick in. The first priority? Heat and power. We need energy, and we need it fast. The fossil fuels we've extracted from the earth, coal, oil, natural gas, these are all stored solar energy, ancient sunlight trapped in organic matter. We'd burn through these reserves as quickly as possible, not wastefully, but necessarily, to power heating systems and grow lights and the infrastructure of survival. Nuclear power would become critical. Fission reactors don't need sunlight. They derive their energy from splitting atoms. Nations with nuclear capability would find themselves at a sudden advantage, able to provide power for heating, lighting, and food production long after fossil fuels ran out. But both of these are stopgap measures, temporary solutions. Eventually, fossil fuels would run out. Even nuclear fuel would eventually be depleted. We'd need something more sustainable, more permanent. And here's where it gets interesting. Earth has a power source that doesn't come from the sun. Deep beneath our feet, the Earth's core is hot, incredibly hot. It's a remnant of the heat from Earth's formation, plus the heat generated by radioactive decay in the planet's interior. This geothermal energy exists independent of the sun. Geothermal power plants could theoretically keep running even after the sun disappeared. The heat from Earth's core could be tapped to generate electricity, to heat buildings, to power the machinery of civilization. Iceland, which already gets a significant portion of its power from geothermal sources, might suddenly become one of the most valuable pieces of real estate on Earth. Any location with access to geothermal energy would become a refuge, a place where humans might huddle together and maintain some semblance of technological civilization. But even with power, we face another enormous challenge: food. The entire food chain depends on the sun. Plants use photosynthesis to convert sunlight into chemical energy. Herbivores eat plants. Carnivores eat herbivores. Humans eat everything. Remove the sun and the whole system collapses. Within days, plants would begin to die. Without photosynthesis, they'd exhaust their energy reserves and wither. The grass would turn brown, trees would shed their leaves, crops and fields would freeze and die. The great forests, the Amazon, the taiga, the rainforests of Southeast Asia would become graveyards of frozen wood. Within weeks, herbivores would starve. Without plants to eat, cattle and deer and rabbits and every grazing animal would exhaust available food sources and die. Their bodies would freeze before they could even decompose. Within months, carnivores would follow. Wolves and bears and big cats, finding no prey, would either starve or cannibalize each other until none remained. But humans could adapt. We'd have to rely on stored food initially, canned goods, dried foods, frozen foods, but these would run out quickly. 7 billion people need a lot of food, and our just-in-time supply chains aren't designed for apocalyptic scenarios. The solution would have to be artificial agriculture. Grow lights powered by geothermal or nuclear energy, creating artificial farms and underground facilities. Hydroponics and aeroponics, growing plants in controlled environments where every variable, light, temperature, nutrients is carefully managed. It would be incredibly energy intensive, inefficient. A single kilogram of wheat grown underground with artificial light would require vastly more energy than the same wheat grown in a sunny field, but it would be possible. Difficult? Expensive? Requiring a complete reorganization of society around survival rather than comfort, but possible. Some scientists have even suggested that life in the deep oceans might continue. There are ecosystems near hydrothermal vents, cracks in the ocean floor where superheated water rich in minerals gushes out that don't depend on sunlight at all. These ecosystems get their energy from chemosynthesis rather than photosynthesis, using chemical reactions to produce energy. Strange creatures live there: tube worms, blind shrimp, archaea that can survive in boiling water. These life forms would be completely unaffected by the sun's disappearance. They'd continue living in the dark, in the deep, utterly ignorant of the catastrophe happening above them. Could humans learn to harvest these deep-sea resources? Could we establish submarine colonies near hydrothermal vents, drawing energy and nutrients from the Earth itself rather than the sun? It's a wild idea, science fiction almost, but not impossible. Given enough desperation, enough ingenuity, enough time, humans might remake themselves into something new, a species that lives without sunlight, that derives its energy from the planet's core, that builds a new kind of civilization in the permanent dark. But it would be a drastically reduced population. 7 billion people couldn't survive this transition, not even close. Maybe a few million, clustered around geothermal sites and nuclear power plants, carefully managing every calorie of food, every joule of energy. It would be a strange, sad, diminished existence. But it would be existence.
Now, let's step even further back. Let's think about what this thought experiment really means. What it teaches us not just about physics, but about existence itself. Because here's the thing. This isn't really about the sun disappearing. The sun won't disappear, not for billions of years. And when it does die, it will be a slow process of expansion and cooling, not a sudden vanishing. This thought experiment is about something else entirely. It's about dependence, about fragility, about the invisible threads that connect everything to everything else. We live our lives with an assumption of continuity. We assume the sun will rise tomorrow because it rose today and yesterday and every day before that, since before humans existed. We assume the air will be breathable, the water will be liquid, the ground will be solid beneath our feet. These assumptions are so fundamental that we don't even recognize them as assumptions. They're just reality, the baseline, the way things are. But they're not guarantees. They're contingencies. Everything we take for granted, every breath, every heartbeat, every moment of consciousness depends on a delicate balance of factors, most of which we have no control over. The sun's disappearance is just an extreme example of this fundamental truth. We are not independent. We are not self-sufficient. We are part of a vast web of interconnected systems, and the stability of our lives depends on the stability of systems far beyond our influence. Indigenous cultures understood this in a way that modern industrial civilization has largely forgotten. They understood that humans are not separate from nature, not masters of the environment, but participants in it, dependent on it, inextricably linked to the cycles of sun and moon, season and weather, plant and animal. The sun didn't just provide light and heat to these cultures, it was a relationship. It was respected, honored, incorporated into the rhythm of daily life. When the Lakota performed the sun dance, they weren't just performing a ritual, they were acknowledging their dependence on the sun, giving thanks for its continued presence. What would they think of our modern relationship with the sun? We barely notice it. We spend our days indoors under artificial light. We wake to alarm clocks rather than sunrise. We eat food grown in industrial agriculture that disconnects us from the seasons. We've insulated ourselves from the natural world to such an extent that many of us could go days without seeing direct sunlight and barely notice.
And yet we're still completely dependent on it. All of our insulation, all of our technology, all of our artificial environments, they're just buffers. They're not independents. They're just ways of putting a little distance between us and the natural systems we depend on. The sun's disappearance thought experiment strips away those buffers. It shows us what we actually are: beings of light, creatures of a specific star, utterly dependent on a ball of fusing hydrogen 93 million miles away. There's humility in this realization. Not a depressing humility, not a helpless one, but a kind of cosmic perspective. We're small. Our planet is small. Our sun is an average star in a galaxy of hundreds of billions of stars, and that galaxy is one of hundreds of billions of galaxies. And yet, despite all that vastness, despite all that scale, this particular star matters enormously because it's our star. The one that warmed the primordial soup where life began. The one that powered photosynthesis and created an oxygen atmosphere. The one that allowed complex life to evolve, that allowed humans to emerge, that allowed consciousness itself to arise in the universe. When we look at the sun, even knowing now that we're looking 8 minutes into the past, seeing photons that began their journey before we looked up, we're looking at the source of everything we are. Every piece of food you've ever eaten was grown using energy from the sun, either directly through photosynthesis or indirectly through animals that ate plants. Every breath you take contains oxygen created by photosynthesis, by plants using the sun's energy to split water molecules. Every movement you make is powered by ATP molecules in your cells, which were ultimately created from food which came from the sun. You are quite literally animated sunlight. Sunlight temporarily organized into a complex pattern that can think and feel and wonder where it came from. And 8 minutes is the distance between you and your source. Let's talk about those 8 minutes more deeply. Let's trace the journey of a single photon from its birth in the sun's core to its arrival at your eye. Because when we say it takes 8 minutes for light to travel from the sun to Earth, that's not the full story. That's just the final leg of an incomprehensibly long journey. Imagine you're a photon, a particle of light, born in the nuclear furnace at the sun's core. You're created in an instant of fusion, when two hydrogen atoms slam together under imaginable pressure and temperature, fusing to create helium and releasing energy, releasing you. The sun's core is dense, incredibly, impossibly dense, so dense that you can't travel in a straight line. You bounce. You collide with other particles, electrons, protons, other photons, and each collision changes your direction, scatters you, sends you careening off at an angle. You're trying to escape the sun, to reach its surface, but you're caught in a maze of matter. Each centimeter you travel takes thousands of collisions. It's not a journey. It's a random walk, a drunkard's stumble through the densest material in the solar system. Scientists estimate it takes between 10,000 and 170,000 years for a photon to travel from the sun's core to its surface. 10,000 years minimum. Some photons might take longer than human civilization has existed just to escape the star they were born in. Think about that. The light touching your face right now began its journey before the pyramids were built, before agriculture, before humans had written language or cities or any of the things we associate with civilization. Some of the light might have started its journey when humans were still living in small bands of hunter-gatherers, painting animals on cave walls and telling stories around fires. But once a photon reaches the sun's surface, once it finally escapes that dense stellar interior, it's free. It enters the vacuum of space and travels in a straight line at the speed of light. And that's when the 8-minute journey begins. 8 minutes and 20 seconds across 93 million miles of emptiness. No air, no matter, Nothing to slow it down or scatter it, just straight-line motion at the universe's speed limit. And then it arrives. It enters Earth's atmosphere, scatters through air molecules, which is why the sky is blue. The photon's blue wavelength scatter more than its red ones, and eventually reaches your eye. It strikes your retina, is absorbed by a cell, triggers a chemical reaction, which triggers a neural signal, which travels to your brain, which interprets it as light. The entire journey, from fusion in the sun's core through thousands of years of random scattering across 8 minutes of empty space, through the atmosphere, to your eye, to your brain, all of it so you can see. And this happens constantly, trillions of photons every second. Each one carrying energy, information, warmth, each one the product of nuclear fusion, the conversion of mass into energy according to Einstein's famous equation, E=mc². Every photon is a tiny packet of the sun's mass, converted into energy, sent out into space. The sun is literally losing mass constantly, converting itself into light and heat and radiation, slowly dissolving away to illuminate its planets. Over its lifetime, about 10 billion years total, the sun will convert roughly 0.03% of its mass into energy. That might not sound like much, but it's an enormous amount. The sun loses about 4 million tons of mass every second. 4 million tons converted entirely into energy, into light, into the warmth on your face. And if the sun disappeared, all of that would stop. The fusion would cease. The photons would stop being created, and after that final 8-minute journey, no more light would ever reach Earth from where the sun used to be. We would be left with only the light from other stars. Distant, cold, too far away to warm us or light our days. We would be in darkness. Not because light doesn't exist in the universe, but because our light, our personal star, would be gone.
The story of understanding the sun is also the story of understanding ourselves, our place in the cosmos, our relationship to the stars, the nature of reality itself. For most of human history, people didn't know what the sun was. They knew it was important, obviously. They knew it was bright and hot and far away, but they didn't know it was a star, that it was made of the same stuff as the twinkling points of light they saw at night. The ancient Greeks debated it. Anaxagoras, in the 5th century BCE, proposed that the sun was a giant burning rock, roughly the size of the Peloponnese Peninsula. He was imprisoned for impiety. The sun was supposed to be a god, not a rock. The idea that this sacred object could be material, comprehensible, subject to natural laws rather than divine will, was offensive, dangerous, heretical. But he was asking the right question, even if his answer was wrong. What is the sun made of? How does it burn? Why doesn't it fall down or burn out? These questions would haunt astronomy for 2,000 years. In 1543, Copernicus published his heliocentric model, placing the sun at the center of the solar system instead of Earth. This wasn't just a rearrangement of cosmic furniture, it was a fundamental shift in perspective. Earth wasn't special. Earth was just another planet, orbiting the sun like Venus and Mars and Jupiter. This made the sun special instead. Not a god, but still central, still foundational, the anchor around which everything else revolved. Galileo, peering through his telescope in 1610, discovered something shocking. The sun had spots, dark blemishes that moved across its surface over days. The sun wasn't perfect, wasn't unchanging. It was dynamic, active, a thing that could be studied and measured and understood. Newton, in the late 1600s, used mathematics to describe how the sun's gravity held planets in their orbits. He couldn't explain what gravity was, that would have to wait for Einstein, but he could describe how it worked,
how the sun's mass created an invisible force that reached across millions of miles to keep Earth in its yearly dance. And yet even Newton couldn't answer the most basic question. What makes the sun shine? Where does its energy come from? For centuries, this was a profound mystery. People knew the sun was hot and bright, but they couldn't explain why. If the sun was burning, fuel like a fire, it would have burned out long ago. There simply wasn't enough fuel to keep it burning for the age of Earth, which geologists were beginning to realize was millions or even billions of years old. In the 1800s, scientists proposed that the sun's energy came from gravitational contraction, the sun slowly collapsing under its own weight, converting gravitational potential energy into heat. This theory, proposed by Helmholtz and Kelvin, could account for the sun burning for about 20 million years. Better than simple combustion, but still not enough to match the geological evidence of Earth's age. The answer came from an unexpected direction: Einstein's theory of relativity. In 1905, Einstein published his special theory of relativity, which included the famous equation E equals mc squared. Energy equals mass times the speed of light squared. This equation revealed something profound. Mass and energy are interchangeable. Matter can be converted into energy, and a tiny amount of matter can produce an enormous amount of energy because the speed of light squared is such a large number. But even Einstein didn't immediately realize this explained the sun. That insight came from Arthur Eddington, a British astrophysicist in 1920. Eddington proposed that the sun was powered by nuclear fusion, hydrogen atoms fusing together to create helium, with a tiny amount of mass lost in the process and converted to energy according to E equals mc squared. Other scientists were skeptical. The temperatures required for fusion seemed impossibly high. But Eddington persisted, famously saying, "If your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. But if your theory is found to be against the Holy Bible, then go on with your theory. The Bible has been wrong before." He was right. In the 1930s, Hans Bethe worked out the detailed nuclear reactions that power the sun, the proton-proton chain and the CNO cycle. Nuclear fusion was real. The temperatures and pressures in the sun's core were sufficient, and the energy output matched observations perfectly. Finally, after thousands of years of wondering, humans understood what the sun was: a ball of hydrogen and helium undergoing continuous nuclear fusion, converting mass to energy, burning not with fire, but with the power of nuclear physics. It was beautiful. It was elegant. And it meant the sun could burn for billions of years, 10 billion years total, with about 5 billion years still to go. We weren't going to lose our sun anytime soon, not to burning out, anyway. The sun was stable, predictable, comprehensible. We could calculate its future, model its interior, understand its behavior. This knowledge brought both comfort and a kind of cosmic loneliness. The sun wasn't a god watching over us, caring about our prayers or sacrifices. It was a star, a natural phenomenon, subject to physics rather than theology. And yet there was something profound in that too. The sun didn't need to be a god to be sacred. Its existence, its stable burning for billions of years, the precise conditions that allowed it to warm a planet at just the right distance to support liquid water and life, all of this was remarkable enough without invoking the supernatural. We live in what astronomers call the Goldilocks zone. Not too close to the sun, not too far away. Too close, and the heat would boil away our oceans. Too far, and everything would freeze. Earth orbits at just the right distance for water to be liquid, for life to emerge, for complex chemistry to flourish. This isn't divine providence. It's physics and probability. In a galaxy of hundreds of billions of stars, many of them have planets, and some of those planets are in their own Goldilocks zones. We're special because we're alive and conscious, not because the universe was designed specifically for us. But we're still dependent, still vulnerable, still 8 minutes away from the source of everything we are.
Let's return to our thought experiment. The sun has disappeared. We've passed the 8-minute mark. Earth has flown off into space in a straight line. The temperature is falling. The plants are dying. Now let's think about what happens next, not just physically, but socially, emotionally, civilizationally. In the first hours, there would be shock, denial, chaos. Governments would try to maintain order, but how do you maintain order when the sun has disappeared, when every assumption about reality has been shattered, when everyone, everywhere, is staring at a dark sky where the sun should be? Communication networks would be overwhelmed, everyone trying to call everyone else, to confirm what they're seeing, to ask what's happening, to hear a voice that says everything will be okay. But everything won't be okay. Religious leaders would be overwhelmed with people seeking meaning, seeking explanation. Is this the apocalypse? Is this divine judgment? Different faiths would interpret it differently, some seeing it as punishment, others as test, others as transformation. Scientists would be on every news channel, every podcast, every social media platform, trying to explain what happened, trying to provide information in the midst of panic. But what could they say? That the sun is gone? That we have limited time before everything freezes? That there's no solution, no fix, no way to bring it back? Some people would riot. Some would pray. Some would spend their last days with loved ones. Some would work frantically on survival plans, on underground bunkers, on ways to preserve humanity through the freeze. The economy would collapse immediately. What's the point of money when the world is ending? Stock markets would crash, not that anyone would care. Banks would close. Stores would be looted or abandoned. But there would be cooperation, too. In crisis, humans often show their best qualities alongside their worst. Communities would come together, sharing resources, protecting each other, trying to survive collectively rather than individually. Scientists and engineers would race to implement survival plans. Every nation with nuclear capability would prioritize keeping their reactors running. Geothermal sites would be fortified, turned into refugee centers. Underground farms would be constructed as quickly as possible. But there wouldn't be enough resources for everyone, not nearly enough. Difficult decisions would have to be made. Who gets access to the heated bunkers? Who gets to eat the limited food? How do you choose who survives and who doesn't? These are the questions that haunt every apocalyptic scenario, and they have no good answers, only necessary ones, only tragic ones. Let's say that somehow, through extraordinary effort and sacrifice, a few million humans manage to establish sustainable underground colonies. They have power from geothermal or nuclear sources, they're growing food under artificial lights, they're maintaining technology, preserving knowledge, trying to keep civilization alive in some form. What would their lives be like? Every day would be the same. No seasons, no weather, no variation, just the constant artificial light of grow lamps, the recycled air of closed systems, the carefully rationed food grown in hydroponic tanks. Children would grow up never seeing the sun, never experiencing a sunrise or sunset, never feeling natural wind or rain, never seeing a bird or a wild animal or a tree growing in soil under open sky. They would know these things only from videos, from books, from the stories older generations told. The sun would become mythology to them, a legend of a better time, a lost golden age when humans lived on the surface and food grew in fields and the sky was blue. Would they be sad? Would they mourn what they never had? Or would they adapt, finding meaning and joy in their underground existence, creating new cultures and traditions that made sense in a world without sun? Humans are remarkably adaptable. We can find meaning in almost any circumstance, create beauty in almost any environment, even in the dark, even in the cold, even in the knowledge that the surface world is frozen and dead. Humans would find ways to laugh, to love, to create art and music and stories. But there would be a profound melancholy, too, a sense of loss that would echo through generations. The loss of the sun, yes, but also the loss of Earth as we knew it, the blue planet, the pale blue dot, the jewel of the solar system, with its oceans and forests and diverse ecosystems. All of that would be gone, frozen, dead, a memorial to what was. And Earth itself would continue flying through space, a rogue planet carrying its cargo of surviving humans, getting farther and farther from the position where our sun used to be. Eventually, in millions of years, we might pass near another star. Not close enough to orbit it, probably, but close enough to feel its warmth for a few decades or centuries as we flew past it. What would that be like? To see a sun in the sky again, knowing it's temporary, knowing we'll pass it and return to the darkness. Would it bring hope, or only make the loss more painful?
Let's think about something we touched on earlier, but deserves deeper exploration. The fact that light has a speed, that information has a speed, that reality itself has a speed limit. This is one of the most profound insights of modern physics, and it's something our intuitions struggle with. We live in a world where communication seems instantaneous. You send a text message and it arrives immediately. You make a video call and see someone's face in real time, even if they're on the other side of the planet. But it's not truly instantaneous. Those signals travel at the speed of light, and even light takes time to travel. When you video call someone in another country, there's a tiny delay, milliseconds, between when they speak and when you hear them. It's barely noticeable, but it's there. Now scale that up. The moon is about 1.3 light seconds away from Earth. When astronauts on the moon communicated with mission control, there was a 2.6-second delay for each exchange. 1.3 seconds for the signal to reach the moon, 1.3 seconds for the response to come back. You can hear this in the Apollo mission recordings, these long pauses between question and answer. Mars, at its closest, is about 3 light minutes away from Earth. When we send commands to rovers on Mars, we have to wait at least 6 minutes for any confirmation. 3 minutes for the signal to arrive, 3 minutes for the response to come. If something goes wrong, if the rover encounters an obstacle or a problem, we can't respond in real time. By the time we know about the problem, it's already 3 minutes in the past. The nearest star to our sun, Proxima Centauri, is 4.24 light years away. If someone on a planet orbiting Proxima Centauri tried to send us a message, it would take more than 4 years to reach us. And our response would take another 4 years to reach them. A single back-and-forth conversation would take nearly 9 years. This is one of the fundamental barriers to interstellar communication, to space exploration, to any kind of galactic civilization. The speed of light isn't just fast, it's the universe's speed limit. Nothing can go faster. Not matter, not energy, not information. Einstein's special relativity proved this. As you approach the speed of light, strange things happen. Time dilates, it slows down for you relative to people who aren't moving as fast. Mass increases. The energy required to accelerate you further approaches infinity. The speed of light is an asymptote, a limit you can approach but never reach, if you have mass. Only massless particles, photons, the particles of light, can travel at light speed. And they always travel at light speed. They can't slow down, can't speed up. From a photon's perspective, if photons had perspectives, no time passes at all. A photon created in the sun's core and absorbed in your eye 8 minutes later experiences 0 time. To the photon, its creation and destruction are simultaneous. But to us, to beings made of matter, time passes. And the speed of light creates an absolute limit on how quickly information can travel. This means the universe is fundamentally fragmented. There's no such thing as now that applies everywhere. Now is relative, local, limited by the speed at which information can propagate. When the sun disappeared in our thought experiment, it doesn't disappear everywhere simultaneously. It disappears first at its own location. Then, 8 minutes later, it disappears from Earth's perspective. 16 minutes after that, it disappears from Mars's perspective, when Mars is on the same side of the sun as Earth. Hours later, it disappears from the outer planets' perspectives. Each location has its own now, its own present moment, and these present moments can't be synchronized faster than light can travel between them. This creates a strange situation. For 8 minutes after the sun disappeared, someone looking at Earth from the sun's location, if they could somehow exist there, would see Earth still orbiting, still bathed in sunlight, still completely unaware. They'd be watching the past. They'd be watching a planet whose sun had already disappeared, but the planet wouldn't know it yet. It's like watching a movie where you know what happens next, but the characters don't. Except it's not a movie, it's reality. The past and present coexist, separated by distance and the speed of light. This is why astronomers say that when we look at distant objects, we're looking back in time. The Andromeda Galaxy is 2.5 million light-years away. So when we look at it, we see it as it was 2.5 million years ago. If Andromeda exploded tomorrow, from their perspective, we wouldn't know for 2.5 million years. The universe is a museum of history. Every observation a glimpse into the past, the present moment forever unreachable, beyond our immediate vicinity. And this means that somewhere in the universe, about 8 light minutes away from where our sun used to be, the sun still exists in the only way that matters for observation, as light, as information, still traveling through space, still carrying the image of a star that exists no longer. In a very real sense, the sun would continue to exist in expanding shells of light, growing more distant and faint, carrying the memory of what was to ever more distant locations, until eventually those photons are absorbed or scatter into the darkness and the sun is finally truly gone from the universe, not just as matter, but as light, as information, as observable reality.
There's a philosophy called cosmic nihilism that says the universe is meaningless, that humans are insignificant, that nothing we do matters in the grand scheme of things. The sun disappearing thought experiment seems like perfect evidence for this view. Here we are, 7 billion people with our cultures and histories and dreams and fears, and a single stellar event, an impossible event, but bear with the metaphor, could wipe it all out. We're completely at the mercy of cosmic forces beyond our control. But I want to offer a different perspective. Yes, we're dependent on the sun. Yes, we're vulnerable. Yes, in the vast scale of the universe, Earth is tiny, and humanity's existence is brief. But meaning doesn't require permanence. Significance doesn't require invulnerability. Think about a beautiful piece of music. It exists only for minutes, only while it's being played, and then it's gone, surviving only in memory and recording. Does this make it meaningless? Does this make it insignificant? Of course not. The temporary nature of music is part of what makes it precious. If music lasted forever, if every song played continuously and never ended, music would lose its power, its beauty, its ability to move us. The same is true for human life, for human civilization, for everything we create and experience and are. We exist for a brief moment in cosmic time, a few million years as a species if we're lucky, a few thousand years as a civilization so far, a few decades as individuals. This brevity doesn't diminish our significance. If anything, it enhances it. Because we know we're temporary, we can appreciate what we have. We can find meaning in the everyday moments. A sunrise, while we have them. A conversation with a friend, the taste of good food, the comfort of being warm and safe. The sun disappearing thought experiment shows us how much we depend on things outside our control, yes.
but it also shows us how remarkable it is that those things are stable, that the sun does keep burning, that Earth does orbit at the right distance, that the conditions for life have persisted for billions of years. We're not lucky. Luck implies chance, and in a universe with billions of stars and planets, life arising somewhere is probably inevitable. But we're fortunate to be alive, to be conscious, to be able to look up at the sun and understand what it is, how far away it is, how it works. That understanding is itself a kind of miracle. For billions of years, life existed on Earth without comprehending the sun. Bacteria and plants and animals used sunlight without knowing what it was, where it came from, how long it takes to reach Earth. Only in the last few centuries have humans understood these things. Only in the last few decades have we had the full picture. Nuclear fusion, relativity, the speed of light, the entire framework that lets us imagine what would happen if the sun disappeared. We live in a brief, precious window of understanding. We're possibly the only species on Earth that can comprehend our dependence on the sun. We can appreciate it, study it, create art and poetry and philosophy inspired by it. If the sun did disappear, if humanity faced extinction, that understanding wouldn't save us physically, but it would matter in another way. It would mean that for a brief moment, the universe was able to understand itself, that matter organized into humans, and humans organized into scientists and artists and philosophers, and through that organization, the universe became self-aware, able to contemplate its own workings. We are the universe's way of knowing itself. We are stardust that learned to think, to wonder, to ask questions about where we came from and where we're going. This doesn't make us invulnerable. It doesn't protect us from cosmic events or guarantee our survival, but it does make us meaningful. Not because we're permanent, but because we're aware. Not because we control the universe, but because we can understand it.
Before we move toward our conclusion, I want to spend some time with beauty. Because the sun isn't just a ball of fusing hydrogen. It's spectacular, dynamic, constantly creating phenomena of breathtaking beauty. Consider a sunrise. You've seen thousands of them probably, and yet each one is unique. The angle of the sun, the composition of the atmosphere, the dust and water vapor in the air, all of these combine to create a particular quality of light that exists only at that moment, in that place. The ancient Egyptians weren't wrong to worship the sun. They lacked the scientific framework to understand nuclear fusion, but they understood something profound. The sun's daily journey across the sky is worthy of reverence, of attention, of awe. When you watch a sunrise, you're watching light that traveled for 8 minutes through space, then scattered through Earth's atmosphere. The red and orange colors you see are the result of Rayleigh scattering. Shorter wavelengths, blue and violet, scatter more easily than longer wavelengths, red and orange. So when the sun is near the horizon and light has to travel through more atmosphere to reach you, the blue light scatters away and the red light comes through. It's physics, but it's also beautiful. These two things aren't contradictory. Understanding how something works doesn't diminish its beauty. If anything, it enhances it. Consider the aurora borealis, the northern lights. These aren't caused directly by sunlight, but by solar wind, charged particles streaming from the sun, taking about 3 days to reach Earth, then colliding with molecules in Earth's upper atmosphere, causing them to glow. The sun is constantly emitting this wind, this stream of charged particles. Earth's magnetic field deflects most of it, protecting us from radiation that would otherwise sterilize the surface. But at the poles, where the magnetic field lines converge, some particles funnel down into the atmosphere, and the result is one of nature's most spectacular light shows.
green and red curtains of light dancing across the sky. Ancient peoples saw these and created mythologies. The gods were fighting or dancing or sending messages. They were right in spirit, if not in detail. The aurora is a message, just not from gods. It's a message from the sun, carried by particles across millions of miles, saying, "I am here, I am active, I am alive." Solar eclipses are another phenomenon of profound beauty. When the moon passes directly between Earth and the sun, blocking the sun's bright disk and revealing the corona, the sun's outer atmosphere, it's a moment of cosmic alignment that humans have watched with awe for millennia. The corona is always there, but we can't see it normally because the sun's surface is too bright. During an eclipse, with the surface blocked, the corona becomes visible, a pearly white halo surrounding the dark disk of the moon with streamers and loops extending millions of miles into space. Ancient peoples feared eclipses, saw them as omens. Some cultures thought a dragon or monster was eating the sun and would make noise to scare it away. But they also recognized eclipses as moments of power, of transformation, of connection to cosmic forces beyond human control. Modern astronomy has stripped away the supernatural interpretation, but not the sense of awe. When you watch a total solar eclipse, you're witnessing a geometric coincidence. The moon is 400 times smaller than the sun, but also 400 times closer, so they appear the same size in the sky. This coincidence exists only during this brief period of Earth's history. Billions of years ago, the moon was closer and appeared larger. Billions of years from now, it will be farther away and will no longer completely cover the sun's disk. We live in the brief window when perfect total solar eclipses are possible. Another piece of temporal luck. Another reminder that our experience of the universe is contingent, temporary, precious. Sunspots are another phenomenon of solar beauty. These are cooler regions on the sun's surface, created by magnetic field lines breaking through from the interior. They appear dark only by contrast. They're still thousands of degrees and would glow brightly if seen in isolation, but next to the even brighter surface, they look like dark spots. Galileo observed sunspots through his telescope and realized the sun was rotating. He could watch the spots move across the sun's disk over days. This observation challenged the prevailing belief that the sun was perfect and unchanging. No, the sun is active, dynamic, a roiling ball of plasma with magnetic fields that twist and tangle and sometimes erupt. Solar flares and coronal mass ejections, these are eruptions of energy and matter from the sun's surface, blasting billions of tons of plasma into space at millions of miles per hour. When directed at Earth, they can disrupt satellites, power grids, and communications. The Carrington event of 1859 was the most powerful solar storm on record, causing aurora visible as far south as the Caribbean and disrupting telegraph systems worldwide. The sun is not gentle. It's not tame. It's a star, burning with the power of billions of nuclear bombs every second, occasionally hurling that power into space in bursts that could devastate our technology if we're not prepared. And yet, for all its violence, for all its power, the sun is also stable. It's been burning at roughly the same brightness for billions of years. It will continue burning for billions more. This stability, this reliable, steady emission of energy is what makes life possible. A more variable star would be catastrophic. If the sun's output fluctuated significantly, Earth would swing between freezing and boiling, making complex life impossible. But our sun is a main sequence G-type star, stable and consistent, providing the steady conditions life needs to evolve and thrive. We won the cosmic lottery. Not just a sun, but this sun. Not just a planet, but a planet at the right distance. Not just life, but complex life, conscious life, life that can look up and understand what it's seeing.
Let's talk about something more personal now. Let's talk about how the sun affects you individually, psychologically, emotionally. You probably don't think about the sun much in your daily life. It rises, it sets, it provides light and warmth, and you go about your business. But your body knows about the sun. Your mind knows about the sun, even if you're not consciously aware of it. Your circadian rhythm, the internal clock that regulates your sleep-wake cycle, is synchronized to the sun. When light enters your eyes, it triggers signals that tell your brain it's daytime, time to be alert. When darkness falls, your brain produces melatonin, a hormone that makes you sleepy. This isn't cultural. This isn't learned. This is biology, hardwired into your nervous system over millions of years of evolution. Your ancestors lived by the sun's schedule, and so do you, even if you try to override it with artificial light and alarm clocks. People who work night shifts, who sleep during the day and stay awake at night, often experience health problems. Disrupted circadian rhythms are linked to increased rates of obesity, diabetes, cardiovascular disease, and depression. Your body wants to sync with the sun, and when you fight against that, there's a cost. Seasonal affective disorder, which we mentioned earlier, affects millions of people. During winter, when days are short and sunlight is scarce, some people experience depression, fatigue, loss of interest in activities they normally enjoy. The treatment? Light therapy. Sitting in front of bright lights that mimic sunlight, essentially tricking your brain into thinking it's summer. This isn't psychological weakness. This is neurobiology. Your brain needs light. It needs the spectrum and intensity that sunlight provides. Without it, your brain chemistry changes. Serotonin levels drop. Melatonin production increases inappropriately. Your mood darkens along with the days. Now imagine that permanently. Imagine no more sunlight, ever. Imagine only artificial light, only the limited spectrum of LEDs and fluorescent bulbs. Would humanity, huddled in underground bunkers after the sun disappeared, suffer from a collective permanent seasonal affective disorder? Would depression become the baseline, the new normal? Maybe. Or maybe humans would adapt. Maybe our brains would recalibrate, finding new baselines, new ways to regulate mood without sunlight. But it would be a profound change, a fundamental alteration of what it means to be human. Beyond circadian rhythms, the sun affects us in other ways. Vitamin D production requires UVB radiation from sunlight hitting your skin. Without it, you develop deficiency, weakened bones, increased susceptibility to disease, muscle weakness, fatigue. Humans evolved in sunlight, and our bodies expect it. In a world without sun, vitamin D would have to be supplemented, another item on the list of things that used to be free and natural, but now require technology and resources to maintain. There's also the psychological effect of simply seeing the sun, of feeling warmth on your face, of watching sunlight stream through a window. These aren't just pleasant sensations. They're deeply connected to our sense of well-being, our feeling of being alive and connected to the world. Studies show that hospital patients in rooms with windows with natural light report higher job satisfaction and lower levels of stress. Office workers with access to natural light report higher job satisfaction and lower levels of stress. Prisoners in cells without windows have worse mental health outcomes than those with windows. We need to see outside. We need to see the sky. We need that connection to something bigger than our immediate environment. In the permanent darkness after the sun disappeared, sealed in underground facilities with only artificial light, would humans lose some essential part of themselves? Would we become something different, something more mechanical, less connected to the rhythms of nature? Or would we create new meanings, new connections? Would we develop new rituals around the times when grow lights turn on and off, marking the passage of days, even though no real days exist anymore? Humans are meaning-making creatures. We find significance everywhere. We create stories, rituals, traditions to mark the passage of time, to connect us to each other and to something larger than ourselves. The sun has always been part of that meaning-making, but in its absence, we'd create new meanings. Sad, diminished perhaps, but still meaningful, still human.